Hi guys, welcome to the DSC University. I'm Wayne English. Today's video is going to be covering HVAC residential components. This is from a class I did in branch training at our Forest Park location. What we're going to be covering is all of the individual components of residential split HVAC systems: furnaces, air handlers, AC units, and heat pumps. Let's take a look. Alright guys, so today we're going over the HVAC equipment components. So what I've got in here is I've got the parts from a gas furnace, air handler, AC condenser, and heat pump. And we're just going to go over each one of them. I'm going to describe to you, what their function is, what they do, maybe some features of them. If you got any questions, of course, we can talk about that. But just mainly, just going to make sure that, just give you an idea, get you more familiar with all the different parts and pieces. So to start out with the blower motors, so we have three different types of blower motors that we use in our equipment. Over on the left hand side you see the PSC, or permanent split capacitor motor. That's your standard motor. That's what we have used on your standard blower assemblies, your standard condenser fan motors. And the easiest way to recognize it is it has to have a capacitor with it to work. And we'll talk more about the capacitor a little bit later. But that's your standard motor. That's your least efficient motor, your more economically priced motor. As of July of last year, one of the federal regulations went into place so that manufacturers can no longer build gas furnaces with PSC blower motors. So that's why you're seeing new model numbers on the gas furnaces, because now all of our gas furnaces are going to have either the second or the third type of motor. And the second type of motor is the X13 ECM constant torque motor. So just like everything else with the government regulations, the X13 ECM motor is more efficient. Of course, it's also more expensive. So that takes our gas furnaces and adds a couple of $100 to the price of them or so, depending on sizes and all that. So any furnaces that we still had in stock that had the PSC motor in them, we could continue to sell them. The manufacturers just couldn't build them anymore after July 1st of last year. So with the X13 constant torque motor, a lot of people get confused about that motor. It's an electronic motor, and the reason it was named the X13 motor is they developed this motor back in 2006 when the industry went to 13 SEER minimum. Before then, all we had was PSC motors and then the higher dollar ECM motors. So they needed a motor that fit somewhere in between that would give you some better efficiency, but didn't cost as much as one of these. And so they developed that. So it's an ECM motor, but it's basically a stripped down version of it. It doesn't have all the bells and whistles. So you get the efficiency of the top of the line motor, but it's closer to the price of your standard PSC motor. So it falls somewhere in the middle there. Then when we get to the top of the line, the ECM motor, it's an electronically controlled motor, and it has all the bells and whistles. You can go in through your either dip switches on the control board or through your thermostat, and you can make all kinds of adjustments with this blower motor. You can do a whole lot more things with it. You can control how it turns on. You can control how it turns off. It ramps up. It slows down. Probably one of the biggest features is they have different controls and different settings where when you're in the air conditioning mode, if the humidity is too high in the house, the blower motor, you can actually make it so it'll slow down a little bit. And when that blower motor slows down a little bit, it moves the air slower across the coil, takes more moisture out of the air, so it dehumidifies better. So besides these increasing, because of the way they work and the way they move the air better, they actually increase the efficiency rating on the outdoor unit, but then you also get the benefit of the better humidity control inside. So we got the PSCs, our X13s or constant torques, and then the full ECM, which they call a constant velocity motor. So this you have your good, your better, and your best. And PSC motors, they'll be around for a long time. They just can't put them in new equipment anymore. So the blower motor is attached to a blower wheel. The blower wheel's been around for forever. Call them squirrel cages, whatever. So just a direct drive wheel connects to the blower, pulls air in the center, blows it out around the circumference. It's going to be mounted in a housing which directs the air up through the furnace or air handler. So nothing really complicated, nothing really new there. So now back to our motors. Our motors have to have capacitors in order to operate. The simplest way to think about a capacitor is an electrical device that stores energy, and when we go to turn that motor on, it releases that energy and gives that motor a kick to get it started turning. A common thing that happens, and I'll use my condenser or heat pump up here as an example, is a lot of times guys will find the outdoor fan motor's not running. And you can take a screwdriver or something and reach in there and spin the fan blade, and the fan motor will start running. And that automatically means that your capacitor's gone bad, because the motor still works, it just doesn't have that kick to get it spinning at the start of the cycle. So we go in there and replace the capacitor, and everything goes back to working like it's supposed to. And they come in different ratings. You see there on the bottom, you've got your MFD rating, which is basically how much kick it gives you, and then you have voltage ratings, which is 370 or 440. So your fan motors are usually going to have your 3.5, 7.5, 10. Then once you get to the bigger sizes, usually you get to your 30s, your 35s, and so on and so forth. Those are going to be found with your compressor. In the furnace, we have an electronic control board. It's called an integrated furnace control. And Rude started using these back in 1992 when Rude went to the 34-inch tall furnace. Before that, they used some circuit boards, but the circuit boards didn't control everything. In 1992, they took all the different relays and a fan center and a fan and limit control. They took all those old mechanical parts and combined them all into one electronic control board just to simplify things. It gives you a lot better control over it, and you have a lot less parts and pieces, a lot less of mechanical parts. So on the control board, you've got, on your left-hand side, you'll see you've got your thermostat wire connections. We've got a fuse on there. Fuse is up above the thermostat wire connection. We have a little display on it that may tell us what mode the furnace is in. It'll display any error codes that may be going on. So got a lot of stuff going on here. So where all your blower motor will wire into here, all your safeties and everything will wire back to the furnace control board. Transformers. Of course, our equipment operates on either 115 volt or 230 volt power, depending on whether it's an AC or a heat pump. Gas furnaces are going to be 115 volts. Air handlers are going to be 230 volts. So within that furnace or air handler, we have a transformer, and what the transformer does is it takes that 115 volts or it's 230 volts, and it reduces it down or drops it down to 24 volts. Then we take that 24 volts and we run that through the thermostat and run it through our safeties and different things like that. So that's called our control voltage. So a little bit safer to work with. That way we don't have 115 volts going to a thermostat up in the living space where somebody can take the cover off and get in there and could get shocked or whatever. 24 volts will still shock you, but it's not going to hurt you that bad. Just catch your attention real quick. And so transformers are rated in what's called volt amps, which means how much strength does it have, how much capacity does it have. And our standard transformers that we have in our equipment are going to be 40 VA, which means if you took that 40 VA and divided it by the 24 volt secondary voltage, it means that you're going to come up with 1.66. So it means that transformer can handle up to 1.66 amps. And typically, without getting into a whole lot of the technical service part of it, usually on just a standard residential setup, going to the thermostat and to the outdoor unit, if you put an amp meter on it, you're usually going to be below an amp. So it's a very low voltage, low amperage control voltage, so it's not dangerous. It's not something that, if you grab hold to it, that it's going to hurt you. And we also have the fuse, which we saw was plugged into the board, the fuse is in the 24-volt side, so if something happens to that, it gets short-circuited or something, instead of burning up the transformer, it'll pop the fuse. One common thing with that is, guy's out weed eating around his outdoor unit, his weed eater gets crazy and he hits the thermostat wire going to the outdoor unit. When it does that, it's going to pop the fuse. So then the system obviously will quit working. You go in there, figure out you got a bad fuse, and you're good to go. Evaporator coils. Rude went to a 3-slab evaporator coil a few years ago. Also went to an all aluminum coil. So our coils have aluminum tubes and aluminum fins. We also carry it as a multi-position coil. So if you look at the coil on the left, we've got a drain pan on bottom, so it can be used in an upflow application. You also see there's a drain pan running up the left-hand side. So I can take that coil and I can lay it down on this left-hand side and blow air through it horizontally, and it still has a pan below it to catch the water that drains out of it. You can see the way the drain connections are located on the bottom left-hand side there. If we wanted to blow air through it the right-hand side way, we actually would just flip that coil around like you would in an air handler. You'd take it out and flip it around, and you'd be able to blow air through it in the other direction. The evaporator coils have the metering device on them. That metering device is either going to be a piston, a thermal expansion valve, or an electronic expansion valve. If you remember back to when we were in here before, the piston or expansion valve is located here at the beginning of the coil. When your refrigerant comes from the condensing unit up through the liquid line to the coil, it hits that metering device, and that metering device basically takes that liquid refrigerant and sprays it into the coil to allow it to evaporate and absorb the heat out of the air. So we have 3 different ways of controlling that, and that's the piston, the thermal expansion valve, and the electronic expansion valve. So on the left, here's what the piston looks like. The piston is basically it's also called a fixed orifice metering device. It's basically just a little device that has a round hole in the center of it. And the diameter of that hole dictates how much refrigerant can go into that coil at a time. These were used in your 10 SEER equipment. Some of it got up into a little bit higher, but mainly just for simplicity, pretty much 10 SEER equipment and older used pistons. They still make some equipment nowadays. We still sell some coils that have pistons on them. But typically the cutoff, when we went from 10 SEER to 12 SEER, you needed to go to an expansion valve to get better control and more efficiency. So we've got the piston on the left, which is basically just a fixed opening, to the thermostatic expansion valve. And the thermostatic expansion valve, it has an opening that's variable. So depending on the conditions, that opening, which is controlled by this spring, this needle valve here, that opening can get larger or smaller. So if there's a bigger load, it can open up more, put more refrigerant into the coil, absorb more heat out of the air. When it's not so, when we don't have such a big demand like today, when it's mild outside, but we still need to run air conditioning on the inside. Then what it'll do is it'll just throttle down. It doesn't need to put near as much refrigerant into the coil because it's not as much heat to absorb out of the air. So that makes it more efficient, because it's not where you can think of the piston is pretty much an on-off switch. You're either getting all or nothing, and then this is more like a accelerator. So you can get a little, get more as you go. Then taking it a step further from that, we have the electronic expansion valve here on the bottom. It does the same thing. It has a variable opening, but it's controlled electronically. So it's controlled a whole lot more precise than what we have with the thermostatic expansion valve. As a matter of fact, on the electronic expansion valve, and I've got some cutaways of them, that opening is maybe 1/8 of an inch in diameter when it's wide open, maybe 3/16 of an inch, and then of course all the way to close. But with the electronic expansion valve, it actually has the capacity to control the size of that opening in 500 steps. So from fully open to closed, there's 500 increments that it can go through. So it gives you extremely precise metering of the refrigerant into the coil. Then when we're talking about a heat pump, our air handler inside, we have an electric heat strip kit. The electric heat strip kit installs in the top of the air handler above the blower assembly. We sell those separately. They come in 5, 10, 15 kW generally, have some other sizes in there. And the electric heat strip kit, it is there for two reasons. One, if the heat pump quits working in the heat mode, we can turn the heat strip kit on, an emergency heat, and use that heat to heat the house. The main purpose is during the winter when we're in the heat mode and it's really, really cold outside, we need some additional heat to supplement what the heat pump can give us. And so the heat strips will cycle on and off periodically to supplement that heat from the heat pump. And basically it's just a package deal that slides into the top of the air handler. Got a couple of screws that mounted in there. It wires into the control board on the air handler. And basically it's just got some switches and relays that turn those strips on and off. The door switch. Door switches are only found on gas furnaces. So if you look at the gas furnace up here, there's our door switch on the upper left hand side. So of course the purpose of the door switch is if this door is left off, that switch is going to open up and it's not going to allow the furnace to run. The reason we have a door switch on the furnace and we don't have a door switch on the air handler is the furnace is a gas combustion device. So if this door were left off, then because we're sucking air in through here, it can actually suck the products of combustion from here back down into the blower assembly and blow it through the house, and we could have a problem with carbon monoxide poisoning possibly. So that's why we have that on there. It's typical, like if I'm out working on a furnace, you take a piece of duct tape, take the door switch shut, so while you're working on it, you don't have to keep putting the door on and off. So, but some guys will bypass them, but that's the reason we have a door switch on the gas furnace and not on the air handler. Also on the air handler, or on the furnace, we have the draft-induced blower. The draft-induced blower is up here at the top of the furnace. It comes on at the beginning of the heat cycle. It pulls air through the heat exchanger, establishes a draft, pushes that air up through the vent going out of the house, and then once the furnace fires up, it also helps to move the products of combustion through the heat exchanger and out through the vent. So it's just a more efficient way of moving the products of combustion out of the heat exchanger. Attached to the draft-induced blower, we have a negative pressure switch. So what if this inducer fails? This inducer fails, we don't want the cycle to continue on, so it's connected by a little rubber hose to the pressure switch. So when that inducer starts up, it's drawing negative pressure, which it pulls some negative pressure through that rubber hose, which makes a set of contacts in this switch. When that set of contacts closes, it allows the furnace to continue on through the cycle. If this fails, or another common thing that happens, birds during the summer like to fly back down, like to come back down through the vent. They'll get in there and they'll die, block the vent off. So when the inducer comes on, if that vent's blocked, it can't push air out. So if it can't push air out, it's not going to draw any negative pressure, so it won't be able to close the switch, and it'll cause the furnace to not operate. And of course, you'd have to have a service call and figure out. Another thing is squirrels. Squirrels like to climb back down in the vent too. They'll get in there, they'll die, and stop it up. Yeah. Another thing, on some of the older models before 1992 that had pressure switches, guys would just go in there sometimes and they would just take the wires off the pressure switch and jump them out, which would set up a condition where that furnace could potentially just sit there and run forever, regardless of what's going on. So it's very dangerous. So now, because the pressure switch is wired back to that circuit board, the circuit board has logic built into it to where it knows that pressure switch has to be open before the cycle starts, and then it closes after the cycle starts. So if that board sees that somebody's jumped that switch out, it'll throw an error code that won't allow the furnace to run. So they have that safety built in there in the logic of the control board. We would test the negative pressure switch out here. I've got a digital manometer teed into the rubber hose so I can actually see what negative pressure is being pulled and determine whether I've got a problem with the inducer or a problem with the negative pressure switch itself. Because what can happen over time is these inducer motors, just like any other motor, the bearings start to get bad, the motor starts to get weak, and it's not spinning as fast as it was designed to, so it's not moving enough air, and so it won't close the pressure switch. So by testing, and there's several different steps to it, I can then determine, do I have a problem with the motor or do I have a problem with the pressure switch? Now we've gotten along that far, now we got to light the fire. So we have a couple of different methods for lighting our burners in the furnace. On the top left, we've got hot surface igniters. Hot surface igniters have been around since late 80s or so. And basically the hot surface igniter is just powered by 115 volts. It heats up to 2400 to 2500 degrees. When you turn on the gas, that hot surface igniter will light the gas. They work. Back in the day, they were terribly unreliable, fragile. If you looked at them the wrong way, they would break. Guys were having, I know back in the day when I worked in parts and worked on the counter, we used to buy those things, thousands of them at a time. Because, every guy, guys probably kept 5 or 6 of them on their truck all the time anyway. You probably tell me, how many of those we sell now? We still sell a pretty good bit, yep, but not nearly like we did back in the day. And I would be willing to say that if you took one of today's and one from 15 years ago, the one today is probably way stronger and way more reliable and durable than that old one was. So some years ago, and spark ignition has been used on and off all throughout years, but years ago, Rude made the decision to go to direct spark igniters, which basically means that this spark igniter is mounted right in front of the gas burner. So just kind of like on your barbecue grill at home, you got a burner in the bottom and you have a little sparker down in there, and you push the button and that little sparker will spark. Well, this is doing the same thing. It's lighting directly to the main burner. So these, you have basically no moving parts. They're very reliable. They don't normally fail. Usually the electronic part of them will fail before the actual part itself, unless something happens to the wire. The insulation gets damaged, something like that. These are way more, and also these start sparking right away, so you can get the burner lit a lot faster. Your hot surface igniter, they would take anywhere from 30 seconds to a minute just to heat up to 2400 degrees. So from the time the thermostat said I want heat, time you turn the inducer on, pressure switch closes, now we got to wait for that igniter to warm up, now the burner's got to light, now we got to wait for the blower to come on. It could be 2 to 3 minutes before you ever get hot air coming out of the vents with a hot surface igniter. So the sparker eliminates that delay, so we get actual heat coming out of the vents faster after the thermostat says, makes a call for heat. The gas valve, located right here. That's where our gas pipe comes into the furnace, goes into the gas valve, out of the gas valve to the burners. Gas valve is a 24 volt operated solenoid, so we have gas coming in from the meter, and it's sitting there ready. Whenever the thermostat says, all right, I want heat, the control board, once we go through all the steps of the sequence, we'll send 24 volts to that gas valve. Gas valve will open up, then we can light the flame and continue on. I got this little picture down here on the bottom just to show you how a gas valve works inside. And the thing about gas valves is they're what's called a fail-safe device, which means if it fails, it's going to fail to the closed position. It's not going to fail to the open position where it could just sit there and let gas come out uncontrollably. So the way that works is, if you look at the blue line on the left, as the gas comes in, here's the solenoid, the plunger of the solenoid that moves up and down. When it's down, it's in the closed position. And then it's got a spring that's holding it down. The solenoid up here pulls it up. So when that gas pressure is coming in, the gas pressure is actually pushing down on the plunger. So when the solenoid is energized, the plunger is actually having to come back up against incoming gas pressure. So let's say the regulator failed outside at the meter, and now we've got full pressure coming into the house. That solenoid's not strong enough to open that valve up against line pressure coming in. So that valve will stay closed and protect us from possibly blowing up the furnace. Once it comes through the solenoid, there's another little spring operated regulator here that actually drops the pressure down, so when we actually feed the gas to the burners, it's at a much lower pressure. That's why when we change a furnace over from natural to LP gas, we have to change that little spring out down there to change what pressure the gas operates at, natural gas versus LP gas. So our gas valve is connected to our gas pipe on the inlet side. On the outlet side of the gas valve, we have a manifold, and here the manifold comes around to the burners. On the manifold, we have a number of holes corresponding to how many burners we have, and in each one of those holes, we have an orifice. And that orifice is basically just another metering device, and it's metering how much gas comes out of that hole. The bigger the hole, obviously, the more gas we're going to get in there. So that hole that's drilled in there, you see the number 54, they use a scale, and that number, that 54 it denotes what size that hole is. And the holes, as the numbers change, the holes get bigger or smaller. So 54 is typically the size of a natural gas orifice in a rood gas furnace. So here we've got 3 burners, 3 orifices. Same thing, if we were changing this furnace to LP gas, we would take those orifices out, put the ones from the LP kit in there, which would actually have smaller holes in them because we use less LP gas than we do natural gas to get the same amount of heat. Then we've got burners that are connected to the manifold. So we've got our gas valve, our manifold, our orifices, then the gas goes into the burners. When the gas goes into the burners, you see there's a little window opening there in the burner. That allows air to come in and mix with that gas. So part of combustion is, what do we have to have? We have to have air, fuel, and ignition. So we've got our fuel coming in from the orifices, we've got our air coming in through the burners, and when that lights, of course, we got a nice blue flame. So the way it's set up in the furnace, and here again, this is another one of those fail-safe things that they have designed into the furnace. They'll have the spark igniter on one side of the burner rack, they'll have the flame sensor on the other side of the burner rack. So when that spark igniter lights, it's going to light the first burner. That flame is then going to carry over to the second burner and light it, carry over to the third burner and light it, and then that's where our flame sensor is located. So if something happens, and let's say only that first burner lights, I'm not going to get any flame over to the flame sensor, so the furnace is going to shut down. You know, it's not uncommon, especially at the end of summer, when somebody goes to start their furnace up for the first time, they don't want to light a lot, because things like these little bitty spiders will get in there and they'll put spider webs inside of those orifice holes, and they'll block it up enough to where the gas can't come out. So you may have one burner light, the second one won't, the third one could light, but because the flame can't carry over and get to the sensor, it's going to shut down, and it's going to, you're going to have a service call to figure out what's going on. Or Another common thing that can happen is there again, your regulator can fail at the meter and fail to a point where it's not giving you enough gas pressure. If the gas pressure is too low, when the gas valve opens up, there may be only be enough gas to light that first burner. There's just not enough volume of gas coming into the burners for all of them to light at one time. And so in that case, the furnace would shut down. So once our burners light, the flame coming off the burners goes into these bottom tubes on the heat exchanger. And the way it works, the flame comes in through these bottom holes, through these tubes up here to a collector box, and then back and forth through these tubes, and then our inducer is mounted here, which is pulling air through the entire assembly. So as all these tubes heat up, our blower assembly is then going to blow air across those tubes, which have heated up now, and carry that heat into the house. Rude's heat exchangers are great. They rarely ever fail. The way the design of them, they're made. They use some stainless steel components in them. Most of it's aluminized steel. There's not any mechanical fasteners. There's not any rivets or screws or anything that hold it together. It's swedge fittings, and you can see how the back of the collector box up there is crimped over. So these things are just, they're back in the day before Rude went to this type of heat exchanger, they used what was called a clamshell heat exchanger, which were these big metal, basically like, there was just two pieces of metal that were riveted together. And we used to stock those things, tons of them, because those things, they rarely would ever last 10 years. Because he had at least a 10-year warranty on the heat exchanger, so people got those on a regular basis. Now our heat exchangers, say now, since '92 when they came out with this furnace design, they have a 20-year heat exchanger warranty, and we rarely ever warranty a heat exchanger. So here's the whole setup, or another step to it. We've got our burners firing into our heat exchanger. We've got our blower assembly blowing air across the heat exchanger. Well, what happens if the blower motor fails? Or what happens if the capacitor fails and the blower motor doesn't start?
Yeah, reset.
We have this switch up here, which is a thermal limit, and it's mounted in the upper right hand corner on this picture, and it just sits out there in the airstream above the heat exchanger. And if there's no air blowing across that heat exchanger to move the heat out of it, that heat exchanger will keep getting hotter and hotter and hotter and hotter, and eventually it'll trip this limit. When it trips that limit, everything's going to shut down. We also have these manual reset limits on the left, and let's say something even worse happens, the heat exchanger cracked, or the heat exchanger got stopped up somehow, and the heat can't go in, the fire can't go into the heat exchanger, and those flames actually start burning out in this direction. If those flames start to roll back out in this direction, those manual reset limits will get hot. They'll open up and they'll shut the furnace down, so we don't have fire coming out the front of the furnace. Another cause of that is, remember, we have to have air to mix with our gas. If this is put in a room that is extremely tight, let's say it's in a utility closet that's extremely tight, we're not getting enough combustion air in there, that flame will actually start looking for air. So it'll actually start coming back out of the heat exchanger looking for air to burn. And what usually it'll do, if it doesn't trip the limit, it'll usually melt wires and cause the furnace to shut off. Yeah.
Back in the day, a lot of times when the flame shoot back, they said the chain was cracked.
Yeah, and that's what. Yeah. So if we had a cracked heat exchanger, what would happen is, you walk around here. What would happen is, when you went through the cycle, the burners would come on, and the flame goes into the heat exchanger. Let's say this panel back here had split open. So when the blower assembly comes on and it's blowing air across here, if that has split open, it can that air from the blower assembly would actually start going into the heat exchanger and actually push the flames back out to the front of the furnace in what we call a rollout.
Right.
And when that happens, usually it'll trip these limits out here. You don't see that very much because of the design of the heat exchangers now. So here's the combustion process. We start out with a cubic foot of natural gas, which is equivalent to 1,000 BTUs. We add excess air, 8 cubic feet of nitrogen, and 2 cubic feet of oxygen. In order to achieve complete combustion, that's the recipe that we need to have for complete combustion. For every cubic foot of gas, we need 2 cubic feet of oxygen, 8 cubic feet of nitrogen, and then they just say excess air, so that you've got more air than you need, and then the rest of it can be expelled on through the system. So what do we say we need for combustion? We got to have air, fuel, and spark. So then we have to have our ignition. Once we get ignition, then it goes boom. Hopefully not. So then we start getting our products of combustion. And our products of combustion are 2 cubic feet of water vapor, 8 cubic feet of nitrogen. So that nitrogen just passes through. It's not even being consumed. That excess air just passes through, and then we get a cubic foot of carbon dioxide. So this is complete combustion, because you don't see carbon monoxide in there anywhere, do you? So what happens is, if we have incomplete combustion, instead of producing carbon dioxide, which is one molecule or one atom of carbon and 2 of oxygen, if we don't have enough oxygen available, we'll produce carbon monoxide, which is carbon and 1 atom of oxygen. See the difference between carbon dioxide and carbon monoxide? It's just we didn't have enough oxygen available during the combustion process, and we end up with a dangerous products of combustion instead of complete products of combustion. So, and the reason that would happen is if the burners are dirty, if the flames actually, if they're hitting up against the metal, it'll cause incomplete combustion. So if the furnace is overfired and the flames are too big, there's a lot of different things. The main one is not having enough air coming into the furnace, so it doesn't have enough oxygen to burn, so instead of producing carbon dioxide, it starts producing carbon monoxide, and then that's when it becomes dangerous. And so if you think about it, 100,000 BTU furnace is going to burn, each cubic foot of gas is 1,000 BTUs. So 100,000 BTU furnace is burning a lot of natural gas. If it ran continuously for an hour, it's producing a lot of water vapor as well. That's why when we get up to the 90% furnaces, we have to vent those in PVC pipe, because we produce so much water vapor that it'll actually start condensing back out before it leaves the house, and it runs back down the vent, and then we have a drain to catch it and drain it out, and so on and so forth. Now we get to the compressor. We go to the outdoor unit. We'll talk about components in the condenser and heat pump. Any questions about the inside components, gas furnace, air handler components that we talked about? So with our compressor, Rude's been using scroll compressors, Copeland scroll compressors for many, many years. Got a picture of the compressor on the left. What I have here on the right is Rude also makes, and we use in some of our higher efficiency equipment, they make a 2-stage scroll compressor. On that 2-stage scroll compressor, and I'll show you this, and then when you see the video, it'll make a little more sense. As our scroll is pumping the refrigerant, it's compressing the refrigerant and pumping it through the system. They have a couple little holes drilled in there, and when those holes are open, it means that scroll is not completely full of refrigerant. It's only pumping at part capacity, which means the system's only operating the way they have it said. It's only operating at 67% capacity. When those holes are closed, then it goes back to operating at 100% capacity. So that gives us the ability for that unit to run at 67% when we don't have a lot of demand, and then when we have a higher demand, it can shift up to second stage and give us 100% capacity. Rude uses these compressors in the 16 SEER heat pump and the 17 SEER AC. So that's why you'll find these in the higher efficiency units, because it gives you the ability, just like we were talking about earlier, on a mild day when you don't have big demand in the house, that unit can run at 67% and probably satisfy your call for cooling. Then when it gets to be an 80, 95 degree day, 80, 90 degree day, then you may start out running it first stage, and it runs for a certain period of time and it's not satisfying the thermostat, so then it'll step up the second stage, go up to 100%, and then it can satisfy the thermostat.
What controls the
the thermostat ultimately controls it, and what it does is on a two-stage thermostat, when first stage calls, it would turn it on at this rate, and if dependent, their thermostats, some of them are set up differently. I'll go with the most common. When first, let's say you've got your thermostat set at 75 degrees. So as soon as it gets above 75 degrees, that thermostat's going to call. It's going to turn that unit on in first stage. Well, if at first stage, if it satisfies the thermostat, okay, it's going to cut it back off. If it calls and sits there and keeps running and running and running, and that temperature then creeps up a little higher, then the thermostat knows that, hey, first stage isn't doing it, so then it would energize second stage, which would give us more capacity, and then be able to bring that temperature down. And usually that's either based off, let's say first stage operates at a ½ degree differential, and then second stage kicks in at 1 degree differential. So that gives you a little bit of separation. Some of them, first stage will come on, run for say 5 minutes. And if it hadn't satisfied after 5 minutes, then it'll turn on second stage. So there's different ways of doing it, but ultimately it's done through the thermostat.
Mm-hmm.
So here's a little video that just shows that we're looking down on the top of the scroll. You'll see that one of the spirals stays still while the blue spiral orbits around it, and as it does, it pulls gas in through the outside and spirals it all the way down to the middle, so the circles keep getting smaller and tighter as that gas goes down through there, compressing the gas and then pushing it out through the center, which it actually comes out through the top port there on the compressor, out into the system. So it's a very simple, you have a motor that sits down in the bottom that turns a shaft and makes that scroll move around like this and pump the refrigerant. This gives you a little bit more of a complete exploded view of what's going on inside the compressor. So pull gas in through the bottom left, spiral it around till it gets to the center, and then it actually goes out through a hole in the top of the plate there.
So that is the actual scroll?
Mm-hmm. If you looked at the compressor, the bottom 2/3 of the compressor is just an electric motor standing straight up and down, and it's turning a shaft. Wait till it's turning a shaft, and the shaft has an offset lug at the top, if you will, and so as the shaft is spinning in a circle, that lug is actually going around in an orbit, and it's causing that scroll to go around like that. So there's our shaft running down through the.
I actually thought that it bumped up and down a small distance.
No. So you see the whole 2/3 of the bottom of that compressor is all motor, and it's just turning a shaft. So you really only have a couple of moving parts. You have the shaft of the motor, and you have that one scroll plate. That's all that's really moving in there. Whereas if you go back to your old compressors, which were called reciprocating compressors, they were built like a car engine. You had a horizontal shaft, and it was just like a crankshaft, and you had two pistons that were going back and forth like this, and they had valves that actually would open and close. So there were a whole lot more moving parts and a whole lot more things that could fail on those.
Which is why I thought the scrolls kind of did the same. They're basically pumped.
That's what makes them more efficient, because you got less moving parts. The tolerances are a lot tighter. The volume is more, and versus if you think about a piston, even though there's two pistons in a reciprocating compressor, they're pushing the refrigerant out in pulses every time that piston goes up and down. This one, as that scroll is turning, the gas is moving through it in a constant stream. Even though on the graphics it looked like it was pockets, but it's actually it's a constant flow of refrigerant gas that's moving through that scroll. So it's a lot more consistent. So with the scroll compressors, not having the valves, that was one of the biggest things. Valves used to be that was usually one of the main failures of compressors back in the day, is they would just wear out or break, or because they were basically like they were spring steel valves that just almost like, you ever taken apart a lawnmower engine? Some lawnmower engines use the same kind of valves. They're called reed valves, and they just flap back and forth.
Yeah.
So then also in the outdoor unit we have a condenser coil for the refrigerant. As it goes through the compressor, once it comes out of the compressor as a hot gas, it's pumped over to the condenser coil. The condenser coil is made out of copper tubes and aluminum fins. Root still uses copper tubing and aluminum fins on all their residential split equipment. When you get into the commercial package equipment, they're using all aluminum coils in a lot of those applications. I don't know all of them off the top of my head. The Root still uses copper coils with aluminum fins in the outdoor unit. In the outdoor unit, we have what's called a contactor, and the contactor is basically, it's the relay that turns the unit on. So your compressor's wired to the contactor, your fan motor's wired to the contactor, and when the thermostat calls for cooling, it sends 24 volts out to the outdoor unit, and that contactor, you see the terminals on the side of it there, you see it's got a coil at the bottom. When we energize those terminals with 24 volts, it just closes a set of contacts in there. When it closes that set of contacts, that allows 240 volts to pass through, and the unit turns on. So it's a pretty simple device. You see we have a single pole, a double pole, and a three pole. The single pole is what's going to be in all your standard residential equipment, because you have 240 volts coming in, so all we have to do is just break one side of that 240 volts to keep the unit from operating. So even though the unit's not running, there's still one leg of that 240 volts coming into the unit. So if you're in there messing around doing something, you can still get shocked even though it's not running. Now your double pole contactor, it works the same way. It just breaks both sides of the 240 volts when it's coming in. So when it's de-energized, there's no power from that point on inside the unit. And then on commercial equipment that uses three-phase power, we have a three-pole contactor, and those break all three legs of the three-phase power when it's coming in. We have high and low pressure switches that are mounted in the outdoor unit. Of course, they do just what they say. They protect the unit against high pressure or low pressure situations. Just something, the most common one would be high pressure if the outdoor fan motor fails. If the outdoor fan motor fails, the compressor is going to keep running, and the head pressure is going to keep going up and up and up because we're not moving any air across the coil, and eventually it's going to trip the high pressure switch and shut the unit off. Dirty condenser coil. If you've been cutting your grass and blowing grass clippings into the condenser coil all summer, eventually it's going to get stopped up and you can't pull any air through there. Even though the fan motor is still running, it's going to get hotter and hotter and hotter, and eventually it's going to trip your high pressure switch. Low pressure, we've got a leak in the system, and the refrigerant level's dropping down too low, the low pressure switch will cut the system off. Or if the indoor fan motor fails and we're not moving any air across the indoor coil, your pressures will drop and the low pressure switch will cut it off. On the outdoor units, the split systems, we have service valves. And if you look at it, Here's the service valves mounted here. So we've got, if you think of it, this is the equipment side over here, and this is where you would connect your line set to. And then here's where you would connect your gauge hose to. So this comes with a metal cap on it. On the top, where we open and close it, it has a metal cap on it. So we have a Schrader core. So we take this cap off, and then we could take the Schrader core out. But the Schrader core is, of course, there to keep the refrigerant in. When we screw our hose on it, it presses the Schrader core in, and then we can see pressure on our gauges, just like you got your valve stems on your car tires. So when the unit's shipped, it has refrigerant in it. That refrigerant is on this side. This valve is closed. Even when this valve is closed, this port and this port are still connected. So I can hook my hoses up while the valves are still closed. I can hook my hoses up here, and I can pull a vacuum on the line set and the indoor coil to get all the air and moisture out of it. And then I can even add some refrigerant back in if I want to. Once I open this up with a service wrench, once I open this up, the refrigerant that's inside the unit is going to fill the line set and the coil. Then at any point, if I close that back, now I've got refrigerant on both sides, but it can't move one way or the other. So typically, the only time let's say I needed to change my indoor coil, and I didn't want to lose my charge, I could actually close the liquid line valve down, let the unit continue to run, and it would actually pump all the refrigerant back around and store it in the condenser coil outside. I can then close my other valve. Now all my refrigerant's been moved back outside. I can go pull my indoor coil out or fix a leak or whatever I need to do on the line set in the indoor coil. Once I get that done, I pull a new vacuum, open my valves back up, and now we're ready to go again. Condenser fan motor and blade. Like I said, most all our condensers, except for the 20 SEER units and maybe a couple of other models, all the condensers and heat pumps are going to have PSC fan motors, which means they run with a capacitor. It's a direct drive to a fan blade, so nothing really fancy there. This is actually upside down. All of our fan motors are mounted in there hanging with the shaft down. If you pop this little plastic cap off, there are 4 screws that go into the butt of that motor and just hold it to the grill. In the outdoor units, whether it be an AC or a heat pump, we've got a fan motor that needs a capacitor, and we've got the compressor that needs a capacitor. So just for simplicity and to save space, we can get what's called a dual capacitor, and that dual capacitor has 3 terminals on it. One's common, the other one will go to the fan motor, and the third one will go to the compressor. And so that capacitor actually has 2 ratings on it. You'll have a rating for the compressor and a rating for the fan motor. Let's say just the fan motor side of it fails. We can either replace that whole dual capacitor, or I could actually just go get a single capacitor, connect it to the fan motor, and just disconnect from the dual capacitor that's in the unit. Let's say that's what I had on my truck. I didn't have a dual capacitor on my truck, but I had a single capacitor that was good for that fan motor. I could just put it in there and then abandon that terminal that goes to the fan.
Just leave everything else.
Leave everything else hooked up and just let that dual capacitor just run the compressor.
Okay.
And then we have those what are they called? Turbo capacitors, which have a bunch of terminals on top of them, and you can actually use jumper wires, and you can actually make that capacitor whatever rating you need it to be. And those are just used as an emergency, something that you can put in there until you can go and get the right capacitor and come back and put it in. So that way you can take that one capacitor and you can configure it for whatever you need for that particular service call, put it in there, keep them running, go get the right part and come back and put it in. On heat pumps, because we're running in the heat mode and the outdoor coil will periodically freeze up, we have a defrost control, and the defrost controls are an electronic circuit board. That circuit board also controls other functions. With the current model defrost controls, we have an electronic circuit board and we have two temperature thermistors. So one of those thermistors hangs down below the control box and it's just measuring air temperature. The other thermistor that has the little metal clip on it, it's actually attached to the condenser coil up inside here. So when that unit's running in the heat mode, it's measuring the air temperature, the coil temperature, and it's keeping up with how long that unit's running in heat mode. And it has a complex algorithm that it's using, and based on the temperature of the coil, the temperature of the air, and how long it's been running, it knows when it needs to defrost that coil. So for example, and I don't know what the exact temperature is, when the coil gets to 30 degrees, of course, at that point we should be starting to form some frost. But what if the air temperature is still 50 degrees? Then the logic will tell it that if we've been running for 10, 15 minutes, we're probably we're probably about to turn off, based on what our run time has been. And if we turn off now and it's 50 degrees outside, the coil will naturally defrost. So it prevents it from going into a defrost and wasting energy because it can use just the outdoor temperature to do it. There's a whole lot more going on with that. That's just a simple explanation of it. But the other side is, if the coil has reached 30 degrees and it's 32 degrees outside, then it's going to be more likely to go into defrost a lot faster because it knows, or it's programmed to know that we're going to start producing frost and we need to get it off the coil now. There are also some other items that are wired in there. The low pressure control that we talked about is wired in there, the high pressure control, so all those are actually controlled by the circuit board. We've got some flashing lights on there that tell us what's going on. It can actually indicate with those flashing lights if we're in a low pressure lockout, if we're in a high pressure lockout, if we're in defrost mode. So it can tell us what's going on with that board by those little flashing lights there. The reversing valve. Now, reversing valves, of course, are only in heat pumps. Straight ACs, we don't need them. And what the reversing valve does, it basically allows the heat pump to redirect the refrigerant from one coil to the other. So when we're in the cooling mode, our refrigerant, just a simple way to think of it, in the cooling mode, our indoor coil is the cold coil, our outdoor coil is the hot coil. During the summer, if you walk by your outdoor unit when it's running, you're going to feel hot air coming off of it. Of course, hopefully inside, you're going to feel cold air coming off of this one. So when we go to the heat mode in the winter, we need to swap. So when this reversing valve shifts, it makes this the cold coil, which is outside, and it makes this the hot coil, which is inside. So we're doing the same thing. So that's why you see we have the need for the defrost control, because now it's cold outside and our cold coil is outside. So we have to monitor the temperature of that coil so we don't frost it up. And the way this works is we got 4 tubes. This is coming from the compressor. This is going back to the compressor. And internally in this valve, there's this little slide that goes back and forth, and you can see it has this little coupling, if you want to call it. And at this point, it has these 2 tubes are connected together. When we energize that valve and make it shift, this actually slides over, and now this tube's connected to this tube, and this tube's connected to this tube. And by doing that, it basically just sends the refrigerant in the opposite directions. Or I was sending my refrigerant to the indoor coil first, now I'm going to send it to the outdoor coil first. So it's simple, but it's kind of complicated. This is an actual reversing valve down here that I cut apart, and I actually can use, because the body is brass and the end plates on the slide are steel, I actually have these little magnets. They're really strong magnets, and I can put them on the reversing valve, and I can actually see by the position of those magnets where that valve is inside of the body. Because obviously this is cutaway, so I wouldn't be able to see this normally. And so that allows me to diagnose whether that valve's slid all the way to the left, slid all the way to the right, or the way they usually fail is something will happen and they'll get stuck in the middle. And if it gets stuck in the middle, now all four of these tubes are connected to each other, and the refrigerant can just go wherever it wants to, and it doesn't go anywhere, it just goes in a circle. Yeah.
I have a question. Okay, most times from fall to winter or something, you have problems with defrost on your reverse valve. What causes that? Sometimes it lock up, it won't go from hot to cold.
It could be any number of things. Usually, if these seals in here can get worn over time, if the system hadn't been maintained properly, if it's gotten overheated, these are like a neoprene seal, and they can deteriorate, and that slide just doesn't want to slide, and because you're actually, the slide is actually pushed back and forth from the refrigerant pressure in the system. So we've got a high side pressure and we've got a low side pressure. And what it does is there's some tubes on here you can't see, these little tubes that go to the ends. And what it does is when the solenoid energizes, it directs high pressure gas to one side and low pressure gas to the other, and the differential in pressure causes that slide to go back and forth. So if my charge is not right and I don't have enough differential of pressure, that can make it hard for it to slide back and forth. Things like that. These are, they're something that's, when they work right, they're great, but there's a lot of ways that they can fail.
And there's no servicing those either, right?
That's right. Yeah, you can't get into any of these parts. And I've been doing this for a long time, and I didn't find out about the magnet trick till maybe 8 or 10 years ago. Somebody had shown me that. I was like, it gives you if you know what you're looking at, it gives you the ability to see what's going on inside of that part. Because a common thing that happens, if this thing hangs up in the middle, what's going to happen is your compressor is going to sit there and keep running. But if you look at your gauges, your pressures are going to be equalized because you don't have gas going in the directions it's supposed to go. What it actually ends up doing is the gas is coming out of the compressor and going right back into the compressor. So guys will look at their gauges and they'll say, I got a bad compressor. Come get a new compressor, put it in there, it's doing the same thing. When in reality, it was the reversing valve that was stuck in the middle. So if I take a couple of minutes and I throw magnets on there and I see, okay, that valve's stuck in the middle, now I know my valve's bad and not my compressor. Or the other thing is, if the unit is allowed to continue to run with that valve stuck in the middle, eventually the compressor is going to burn up because it's just sitting there recirculating hot gas back and forth, and eventually it'll fail. So then you can end up with a failed reversing valve and a failed compressor. Welcome back. I hope you enjoyed our video of a training session that I did for branch employees at our Forest Park location. Thanks for tuning in, and be sure to catch more videos from the DSC University.